Hello, welcome back to the playlist of lectures on correlation, simple and multiple linear and nonlinear regression models. I am Hemakumar Kasala. In this fifth lecture in the series, we focus on the topic of simple linear regression models. Since there are too many aspects to learn in this lecture comes in two parts. This lecture focuses on part 1, and in part 1, we understand the shortcomings with the simple linear regression line in capturing the linear relationship deterministically if exists between a bivariate data pair, and introduce the need for a probabilistic model, namely the simple linear regression model. We explain the role of the error part in the above model and the necessary assumptions about the behavior of the error. Explain how the coefficients, the intercept and slope of the population regression line are inferred from the coefficients of the sample regression line, and introduce the model utility test to judge if the simple linear regression model is suitable enough to arrive at acceptable inferences about the population characteristics. Let's get into the video. Revisiting the example that we discussed in one of our previous lectures, the scatter plot and the least squares line, that is the regression line, based on a sample of 37 universities or colleges wherein the regression of the dependent variable graduation rate on the independent variable average per student expenditure is plotted over a period of 6 years. We arrived at a least squares line that was best fitted for the sample data corresponding to the randomly chosen 37 universities as graduation rate equals 17.68 plus 0.003837 multiplied by student-related expenditure. Is the linear relationship thus arrived between the graduation rate and the student expenditure representative of the whole population, meaning for all the universities in the country, or the linear relationship is just a chance outcome as a result of the choice of the sample drawn, which does not represent the population on the whole within acceptable limits of accuracy? If there exists a meaningful linear relationship between the graduation rate and the student expenditure for the whole population that is captured by a population regression line displayed in red, and the sample least squares line represent the population regression line reasonably accurately, then the sample regression line can be used to predict the graduation rate for a chosen student-related expenditure for any university in the country, meaning in the whole population, within a reasonable interval of accuracy. Since the sample regression line depends on the sample data drawn each time, the predicted value of the graduation rate for a selected student expenditure value is not the same each time the sample is drawn. A predicted value for a selected student-related expenditure has two interpretations. The first interpretation, as the name suggests, is a predicted value of an actual graduation rate in the population for a selected value of a student-related expenditure. This predicted value is derived using one sample regression line arrived out of a single sample, and the predicted value can either be above or below a single actual value or each value among a set of actual values in the population for a selected value of a student-related expenditure. The actual value in the above illustration is above the predicted value. The second interpretation is the predicted value also represents the estimate of the mean value of the graduation rates for a selected value of the student-related expenditure, which falls on the population regression line, which is the red line, which in other words is a mean of the predicted values arrived out of various regression lines from all possible random samples out of that population for the selected value of the student-related expenditure. Since the predicted value varies depending on the sample drawn each time, it is essential to qualify the predicted value for a selected student-related expenditure with intervals. The first one of them being the confidence interval for the mean value of the graduation rate, which falls on the population regression line, and the second one being the prediction interval for the actual value of the graduation rate that is either above or below the predicted value. Rest of this lecture and part 2 of this lecture that follows, we develop a probabilistic simple linear regression model using the sample regression line from a single sample. Explain the necessary assumptions to arrive at such a model and check if those assumptions are complied with so that the model is proven reliable and applicable, and derive the confidence and prediction intervals to make the inferences about the population using the model. A sample regression line does not often establish a deterministic relationship within a bivariate pair x and y, that is between the graduation rate and the student-related expenditure in this example case. A deterministic relationship is one wherein the actual value of y is completely determined by a chosen value for x. Determines the actual value of y for every chosen value of x, which implies the predicted value of y is exactly the same as the actual value of y for every chosen value of x. But it is often not the case, since y is influenced by factors other than x in most of the cases. Therefore, a deterministic relationship between y and x is often rare. The predicted value using the sample regression line is often less or more than the actual value for a selected value of x. Therefore, the sample regression line falls short of a deterministic model on its own. On the other hand, a relationship within a bivariate pair x and y is better described by a probabilistic model of the form y equals f of x plus e. This additive probabilistic model has two components. One, f of x, which is the deterministic part, and two, e, which is a random error. While f of x can be the linear regression line expression, that is f of x equals a plus b multiplied by x, where a is the intercept and b is the slope of the regression line, e is a random error that accounts for the deviation between y and f of x for any given value of x. E is a random value for each value of x that allows f of x to be more or less than the actual value of y. An additive probabilistic model y equals f of x plus e, wherein the deterministic function f of x is a linear function as in f of x equals a plus b multiplied by x, is called as a simple linear regression model denoted by y equals alpha plus beta multiplied by x plus e, where alpha replaces a and beta replaces b. The linear deterministic function alpha plus beta x in the simple linear regression model y equals alpha plus beta multiplied by x plus e describe the population regression line, not the sample regression line. Simple linear regression model assumes that there exists a population regression line with an intercept on the y-axis equals alpha and has a slope equals beta. And an observation made on the independent variable y for a selected value of x is given by y equals alpha plus beta multiplied by x plus e. The error e can be positive, negative, or 0 and can be large or small for a particular value of x across repeated sampling or across values of x's in a single sample. Therefore, we need to make some assumptions about the characteristics that the distribution of error e for a particular value of x complies with, such that the simple linear regression model y equals alpha plus beta multiplied by x plus e is deployable and meaningful inferences are made out of the model. Basic assumptions about the distribution of e in repeated sampling at any particular x value. Number 1. The distribution of e at any particular value of x is normal, meaning a sample of data pairs x and y where x is a single fixed value The resulting error E for each of the data pairs exhibit a normal distribution. The distribution of E at a particular value of X has a mean denoted by mu E, which equals 0. That is, mu E equals 0. Basic assumptions number 3. The standard deviation sigma for the distribution of E remains the same for any particular value of X. Number 4. The random deviations E1, E2 and so on until En with different observations at any particular value of X are independent of one another. The randomness in error E implies that the value Y is also subjected to uncertainty to an extent that depends on the variance within the error E. Y equals alpha plus beta multiplied by X plus E has two parts. The first one being alpha plus beta multiplied by X, which is a constant for a particular value of X, say X star. The second part is the error E, which is random, bound by the assumptions that we just discussed. That implies that the distribution of Y with repeated sampling at a particular value of X equals X star is also normal, with mean value being alpha plus beta multiplied by X star, that is the height of the population regression line above X star, and the standard deviation equal to that of the error E, that is sigma. The increase in the average or the mean value of Y per unit increase in X is determined by the slope beta of the population regression line. The y-axis intercept alpha determines the mean value of Y when X equals 0. The standard deviation sigma determine how far typically are the X and Y observations located away from the population regression line. Note, as per our basic assumption, sigma remain the same for any value of X. Smaller the sigma, closer are the observations to the population regression line. That is, smaller are the deviations. Larger the sigma, away are the observations from the population regression line. In other words, larger are the deviations. But the catch is, it's almost impossible to determine the intercept alpha and slope beta for the population regression line. They need to be estimated using a sample. Using the sample regression line, in other words, the sample least squares line. The intercept A and the slope B of the sample regression line turn out to be the point estimates of alpha and beta respectively. Please recall from our previous lecture that slope B of the sample regression line, which is the point estimate of beta, equals Sxy divided by Sxx, where Xxy equals the covariance in the bivariate data pair xy from the sample, and Sxx is the variance in X from the sample. Sxy and Sxx can be calculated using the following formulas, derived keeping in mind the computational ease. Sxy equals sigma x multiplied by y minus sigma x multiplied by sigma y divided by n, and Sxx equals sigma x square minus sigma x the whole square divided by n, where n is the sample size. From our previous lectures, we also understand A, which is the point estimate of alpha, equals y bar minus b multiplied by x bar, where y bar and x bar are the mean values of y and x from the sample. The estimated regression line from the sample is given by y hat equals a plus b multiplied by x. A single estimated value y hat for a selected value of x equals x star equals a plus b multiplied by x star. This value has two different interpretations. The first interpretation is that y hat equals a plus b multiplied by x star is the point estimate of the mean y value for a selected value of x star that falls on the population regression line. The second interpretation is that It is a point prediction of an individual y value for a selected value of x star. While the point estimate or the point prediction is one from a randomly chosen single sample, the mean y value is the mean of such point estimates or point predictions from all possible different samples from the population. Standard deviation of error sigma determines the extent of the spread of the data points x and y with respect to the population regression line. However, since the population regression line is not known, a point estimate of sigma is required and computed using the estimated or the sample regression line and the observed or the sample data points. We compute the residual sum of squares SSR, which is sigma y minus y hat the whole square, to arrive at a point estimate for sigma. We start with estimating the variance in error E, that is sigma square. The statistic that estimates the variance sigma square is denoted by SE square, which equals SSR divided by n minus 2. The subscript E reminds that it is the variance of the errors, in other words the residuals, where n minus 2 is the number of degrees of freedom. The estimates of alpha and beta, that is A and B, reduce the degrees of freedom by 2. Therefore, the number of degrees of freedom equals n minus 2. The statistic that estimates sigma, the estimated standard deviation of the errors or residuals, therefore is SE, which equals square root of SE's square. While sigma represents the typical magnitude of the deviation of the data point xy in the population from the population regression line, SE represents the typical magnitude of deviation of an observation x and y in the sample from the sample or the estimated regression line. Larger SE, away are the observations, and smaller the SE, closer are the observations from the regression line. The coefficient of determination R square discussed in our previous lecture can be computed based on this estimated regression line as R square equals 1 minus SSR divided by SST, where SST is the total sum of squares of the residuals or errors, which is given by SST equals sigma y minus y bar the whole square, where y is the individual y value from the observations or the sample, and y bar is the mean value of the above y values. The interpretation for R square is it is the proportion of the variation in the y values in the observations that is explained by or attributed to the simple linear regression model. The slope beta of the population regression line determines the average increase or the expected increase in the independent variable y when the associated dependent variable x increases by 1 unit. Since the slope beta most of the times is unknown, is estimated using the sample of observations x and y whose size is n. Thus, B, the slope of the sample regression line, turns out to be a point estimate of the slope beta of the population regression line. As with any point estimate, the estimate slope B may be close to the value of the population slope beta or a bit far from beta depending on the random sample chosen. A knowledge on the distribution of the point estimate B provides an insight as to how good an estimate B is. If 4 basic assumptions we discussed about the distribution of error or residuals E about the population regression line are satisfied, then we can assume that the following conditions about the distribution of the point estimate B are met. The point estimate B is normally distributed. The mean of the point estimates or the distribution of B, denoted by mu naught, equals the population regression line slope beta. Therefore, a point estimate B star is an unbiased estimate of the population regression slope beta. The standard deviation sigma B of the distribution of the point estimate B is given by sigma B equals sigma E divided by square root of Sxx, where sigma E equals the standard deviation of the error E about the population regression line and Sxx equals sigma x minus x bar the whole square. Sigma b equals sigma e divided by square root of sxx implies the standard deviation sigma b is larger when the distribution of the error is wider. That is, sigma e is larger and or sxx is smaller. And sigma b is smaller when the distribution of the error is narrower. That is, sigma e is smaller and or sxx is larger. While the variance in y calculated using syy as observed from the sample and variance in x calculated using sxx from the sample decide the slope b of the estimated regression line, the standard deviation sigma e determines the variance in slope b. In other words, the extent of the swing possible for the slope b about the population regression line. Similarly, the variance in x determined by sxx restrict or boost the variance possible in slope b. Larger sxx is, lesser is the possible variation in slope b, and smaller sxx is, larger is the possible variation in slope b. Therefore, beta tends to be more precisely estimated using the point estimate b when the sigma e is smaller and or x values in the sample are well spread out, that is sxx is larger. However, sigma e in sigma b equals sigma e divided by square root of sxx is not known. That is, the standard deviation of the error about the population regression line is almost always not known. Therefore, sigma b is estimated using SE, which is an estimate of sigma e, as in SB, which is an estimate of sigma b equals SE divided by square root of sxx. Since sigma b is not known and is estimated using SE, the standardized variable for b is a t-statistic given by t equals b minus beta divided by SB, and its distribution is a t-distribution with degree of freedom equal to n minus 2. Therefore, when the four basic assumptions for the error distribution E are met, the confidence interval for beta is given by the point estimate b plus or minus t critical multiplied by SB, where t critical is the value for t for a chosen level of confidence interval. Refer lectures on point estimates and confidence interval for more details on t critical value. Confidence interval for the slope of the population regression line beta given by b plus or minus t critical multiplied by SB, when t critical is chosen for a confidence interval of 95%, then 95% of the times, in other words, in 95% of the sampling instances, the population slope b is contained within the interval b plus or minus t critical multiplied by SB. Smaller the standard deviation for the slope b, narrower is the confidence interval, and hence more precise is the estimated value b for the population slope beta. Hypothesis test for beta. Often an hypothesis test about beta is quite useful and in a few cases imminent to verify if the simple linear regression model delivers a useful linear relationship between the dependent and the independent variables, especially when the scatter plot and R-square values are not convincing enough. An hypothesis test that could be carried out has a null hypothesis h0 colon beta equals 0, which states that there is no useful linear relationship between x and y, versus an alternative hypothesis ha colon beta not equal to 0, which claims there is indeed a useful linear relationship between x and y. This hypothesis test is called as the model utility test. This test verifies the utility of the simple linear regression model. Steps to carry out the hypothesis test. A recap for this model utility test. Note, only the steps are listed here. For concepts behind these steps, please go through the previous lectures on hypothesis testing, point estimates, and t-statistic tables. Steps. Calculate the t-statistic, that is, the standardized variable for the sample regression line slope b, which is given by t equals b minus the population regression line slope beta divided by the standard deviation for b, which is SB. Since the hypothesized value for beta equals 0, t equals b divided by SB. Pick the p-value for the above t-statistic from the t-statistic table. Calculate 2 multiplied by p-value, as the t-statistic can either be positive or negative in this case. 2 multiplied by p-value should be compared against the chosen significance level for the test. A widely chosen significance level for hypothesis test is 0.05. If 2 multiplied by p-value is greater than or equal to significance level, the null hypothesis h0 colon beta equals 0 is not rejected. And the conclusion can be arrived that there is no compelling evidence found to suggest that there exists a linear relationship between x and y. And applicability of simple linear regression model is considered not useful in this case. If 2 multiplied by p-value is less than significance level, the null hypothesis h0 colon beta equals 0 is rejected. And conclusion can be arrived at there is indeed compelling evidence to favor the alternative hypothesis HA colon beta not equals 0, which claims that there exists a linear relationship between x and y, and applicability of a simple linear regression model is considered useful in this case. When 2 multiplied by p-value is greater than or equal to significance level, and the null hypothesis h0 colon beta equals 0 cannot be rejected, one should explore the other options. Two of the often used options are: 1. Explore nonlinear models discussed in the previous lectures if the scatter plot indicate any curvature. And 2. Explore a multiple linear regression model. We will discuss on this in our next lectures. That brings us to the end of the part 1 of the lecture on simple linear regression models, which is the 5th lecture in the playlist of lectures on correlation, simple and multiple linear and nonlinear regression models. We discussed the shortcomings with the sample linear regression line in capturing the linear relationship deterministically, and understood the need for a probabilistic model, namely the simple linear regression model. We understood the role of the error part in the above model and the necessary assumptions about the behavior of the error. We learned how the coefficients intercept and slope of the population regression line are inferred from the coefficients of the sample regression line, and understood the model utility test to judge if the simple linear regression model is suitable enough to arrive at acceptable inferences about the population characteristics. See you back with the second part of the lecture. Bye until then.